So let's start today's tutorial. It will be based on some data transfer instructions which we have already learned in the theory class. Okay, so the first problem is like this: write a program to move contents of memory location 0500H to a register BX and to CX. Okay, so the same data requires to be moved to two registers, BX and to CX. Okay, and then add immediate byte 05H. Okay, so that's an this is just a byte, whereas this is a memory location. That is why it is an 16 bits are there. This is just a byte. Okay, and to the data residing in the memory location whose address is computed by DS is equal to 2000H and offset. So you have to calculate the physical address with these things and with these two data, and in that memory location this data 05 needs to be stored. Okay, and then store the result of the addition in 0700H. So the result of the addition, first we add this data into the data which is available in this memory location, and then the result of that addition needs to be stored in 0700. Assume the data is located in the data segment specified segment specified by the data segment register which contain this. Okay, so the first one is pretty easy. First we need to initialize the before we start our program. First we need to initialize DS with 2000, right? So because it's given out here, but we all know that we can't put data directly into the segment registers. So the option available to us is to move it into a general purpose register, and then from there move to DS. So the first two is just initializing the data segment register, where we have moved 2000 to AX, and from AX we are moving it to DX. And then the next option, next thing is to move this data into the BX register and to CX. So we have done no immediate byte write the program. Okay, no, it is the memory location. There is some data available in this memory location. That content needs to be stored to BX and CX. So for that we write within square bracket. So this indicates the memory location. Offset is given here. So that is going to be moved to BX, and from BX we are moving to CX again. So both these registers have been now updated with data available in this memory location. Okay, next is to add 5H to a data which is available in this memory location, so that you can write an immediate operation itself. So this data gets, the data in the memory location gets updated with data whatever was available previously plus 5H, so that gets updated. Then move DX, so that data needs to be now moved to some other memory location. So we don't have an operation from memory to memory direct transfer. Okay, so we need to bring it into one of the common registers out here, and then from the common registers we again push it back to the required memory. So it is again done in two steps. From 6000 we get it to DX, from DX to 7000. Okay, so these are, so why is that two memory locations we can't have simultaneously these things? One, it will be very clear once we see the hardware implementation of 8086, because it is a single address line, right? So you can activate only one memory address at any given time by placing the address of that memory. So if you require memory to memory operation, two memory cells needs to be activated simultaneously, but you have only one set of 20 lines which is available for the memory lines. So that is the reason why two memory lines cannot be activated simultaneously. Okay, so that is the problem there. Okay, now another thing which we have to look at it is why is that we have not done immediate operation here. We could have done CX and then return the same thing within square bracket 5000, where we could have got this data from the memory into the CX. Okay, so there is an, if you see, I will show it in the next slide. In fact, if you see the op code for register to memory to register, it is a 3 byte thing, whereas if you have to do register to register, okay, register to register, it only requires 2 bytes here, within 2 bytes. So the code is pretty smaller if you do register to register transfer. When we write a code, so it will take only 2 bytes, whereas from register to memory it is going to take 4 bytes in fact. So that is the reason we do that. Also, I have not taught you about the timing diagrams, which we will do after the hardware implementation, but just so that it remains at the back of your mind, that we have to also think about the timing diagram. So when we do an register to register transfer, it takes only 2 clock cycles. That because if you see, it is only 2 clock cycles here, somewhere it's written register to register. Okay, exchange, move, register to register, here it takes only 2 clock cycles, whereas from a memory to register, okay, it takes 8 clock cycles. Okay, obviously when we are doing an register to memory transfer, first we need to place the address of the memory on the address bus, and then we have to latch that memory and then again convert that because it is the same address lines, or the data lines are the same, it is multiplexed. So again in the next clock cycle, that address lines will get converted into data line. So you require n number of clock cycles to get the data, right? Whereas register to register is within the 8086 itself, so it doesn't involve your data bus and the address bus multiplexing and demultiplexing. So that is the reason it takes much lesser number of clock cycles. So these are the advantages. Okay, I've just mentioned it, you don't have to remember this right now. Once we learn about these things in the theory class, then these things will be pretty clear to you. Okay, now the second program is write an ALP that transfers a block of 100 bytes of data. The source and destination memory block starts at 8000 and 9000 memory locations respectively. So starting at 8000, you have 100 bytes of data. You need to copy from there and put it into memory location which is starting from 9000. The data segment register is 3000. Okay, so within data segment register itself, we need to transfer from 8000 to 9000. Okay, so how to go about this? Okay, so what is written here is the code segment addresses here, 2000, 2003 and all. So you need to be careful how to progress about this. Like the first instruction is we are going to initialize the data segment. So the first 2 codes are that, lines of the codes are that we are moving 3000 into AX and from AX to DS. So these first 2 just initializes the data segment. Okay, now if you see move AX 3000, it is a 3 byte information which we have learnt in our assembly language to machine language and coding that we have learned. So that is why if you see 3 in the code excuse me, in the code segment, 3 memory space have been consumed. So it from 2000, the next one is going to be 2003. So you got to be careful with these also. So you might lose marks if you are not very correct with this. Okay, in case in the exam, if this is not specified to that you need to write memory location, then you can just write the code. But in case it is specified, then you need to be careful with how you write these data. Okay, so here DS has been initialized with 3000, and now subsequently we need 2 pointers because there are a string of data which is available. So one pointer we use SI, the second pointer we are going to use as DI, right? And then we also require a counter to see to it that 100 bytes of data, so we require some counter. So 100 in decimal is represented as 64 in hexadecimal, so we have initialized a counter. So now we have moved SI, okay, the data which is available in SI, that is the first memory location, into AL, and then we have moved the data which is available in AL into memory location which is specified by DI. So this is 8000 initially, so this is 9000. So what I was telling is, okay, now this the first data gets first data is being fetched to AL out here, and then from AL it is being shifted to location specified by DI, which is 9000. Okay, now for the second data I can increase the SI and increase the DI values. Now it will go to 8001 and 9001. So then you decrease CL, so that we know we have to stop somehow after doing 100 bytes of data transfer. So we decrease CL. After decreasing CL, we check for zero condition. Okay, so we check for zero condition, and then if it is not a zero, then you go back to this move instruction, which is 200D. Again we move this the next data, so it will form a loop out here till the value gets to 0. Continuously this loop would work when all the 100 datas will be transferred, and once it is done, you come out of the loop. Okay, so this is how we write a program here. In case these you need not, if you are asked not to specify these memory locations, then you can give a label out here at instead of 2000B, you can give some label here as label 1, and then you can write jump not z label 1. Okay, so that it jumps there, so that you don't have to write these memory locations. In case if memory locations is to be, has been asked, then you need to be careful. Like increment SI, it takes only 1 byte if you see. Okay, some instructions take 2, like move EF. So this is only taking 2 memory locations, whereas these instructions take 3. So that you will that we know how to calculate whether it's take 2 bytes or 3 bytes. Okay, so this is how we write the program. Okay, now can somebody suggest some modification in this program? Say can I transfer these data as word also instead of byte transfer? Can I do a word transfer? Anybody? Doesn't matter even if it's wrong. Can you just suggest, can I do a word?
So in that case, instead of we'll have to do like memory to register transfer instead of first transferring it to SI and then AL.
No, SI is indicating the memory location, right? Now what if I have to fetch a data from the SI location? Okay, let's take one by one. Okay, like if I have to fetch a data from the same memory location, instead of 1 byte, if I have to fetch a data, what is the change which I need to do in this particular line?
So we can write like move AX and in brackets 8000.
No, I can still write SI.
Okay, yeah, but if you write AX, it will take 1 word instead of a byte.
Yeah, and then I write here also AX, right? So if I, instead of AL, if I replace it with AX, and if I do here AX, it will fetch one data, and it will 1 byte, that is 1 word, that is 2 bytes, and it will push in 2 bytes here. Okay, so this is taken care of. Now we also need to do some changes. So now what about this? Do I have to increase SI 2 times?
Yes, sir. Add +2
Yeah. So
in both and decrease -2.
yeah, these two we need to increase SI by 2 and DI by 2, and we need to decrease CL by 2, or alternatively CL we can feed 32 out here, right? By we can write 32 out here instead of 64, right? Because each time 2 bits. So this is the thing with word transfer. So here I have on CL I have replaced instead of 64 32, and this as AX, and increased SI twice, or increase DI twice, right? You can use the add command also, or you could write increase also, right? Generally you should not write add, because what happens is when you do the add, okay, in these cases, okay, when this is the difference between in yesterday's in fact Yesterday was a holiday, I didn't realize, so I took the class yesterday. And there were some students also who were as absent-minded as me. They also joined yesterday. So there, so I have posted that video, so you can go through that in case you have not. So when we do the increase command, it doesn't affect the carry flag. Okay, so that is the advantage of using increase. So because when we do see, if you see increase here, we are looking for jump not z here. So in some cases, if the carry is say after decreasing CL, here we are stopping in this particular case, but in some cases maybe we want to use the carry which was done during some arithmetic operations above. So we can use that. I think there was an example like that in the theory class. I have explained a specific examples also. So that is generally SI and DI increments, and we should not use add, and we should use the increase command. Okay, as a general rule. Okay, so that helps in certain cases. Okay, so we have increased SI twice, DI, and decreased CL. Okay, so this is second option which we need to do. Okay, so there is no
Excuse me, sir.
advantage in doing this. Yeah, tell me.
So, 2-3 doubts. So, first of all, like by transferring word, would it result in lesser CPU cycles used?
No, that's what I was just coming to. While we see the timing diagram, it may not really because see, it is going to be the how does this data transfer happens actually in the CPU. Okay, first we place an address of the memory location. Okay, and then since the same address bus is going to be used for the transfer of the data also, we will use a latch, and that this data is latched into an 20-bit lines. Okay, and then that particular memory cell will be activated, and then in the next clock pulse that data will be made ready by the memory cell. Okay, in the third clock cycle that data will be placed into the data lines, and then in the next cycle that data lines will be fed into the registers. Okay, it happens byte wise only, because no, probably in the word, in the same cycle 16 data can come, so it will really help in reducing the clock cycle. Yeah.
All right, sir.
Yeah,
So, and
all the
also,
16 lines will be used now. We have 16 data lines, right? So two memory, it is possible for activating two memory lines, two memory cells simultaneously. When we see the hardware, it will be very, very clear. It is going to be a very interesting class on how the hardware is implemented. Okay, so it is possible to activate two memory cells parallelly and fetch an, because we have 16 bit data line, so that word will get transferred. So number of clock cycles required will be half in this case. Yeah.
yes, sir. So, and these memory locations that we are writing, that 2000, 2003, 2005,
Yeah.
we calculate them based, like we first have to calculate the opcode for that and then determine the amount of bytes the opcode takes, right?
Yeah, correct.
So if we are given this question in the exam, we have to calculate the full opcode for each and every command, and then calculate the number of bytes and increase it in that order.
Yeah, you can actually note it down on a paper and keep it early itself. That move register to register will take 2 bytes of data. Move AX will take 3 bytes of data. Right? You don't have to write the opcode every time. Right? Increment takes 1 byte. Decrement takes 1 byte.
Yes, sir, understood, sir.
Correct. So this is standard. It won't change, right? So these things, right? So move AX SI, right, and move DL. This takes 3 bytes of information. So these are only a few standard instructions which you will encounter, right? So if you keep it noted down on a piece of paper, it will help. You don't have to waste your time calculating that. Okay. These are all standard instructions which we see. In case some new instruction you encounter, then you might have to look up. Otherwise, you can make a small table and keep it for reference. Okay.
Understood.
Okay. Now the third one is using loop. Okay. Here what we have done is we use a loop command. Okay, so here if you see in the loop command, here it is cx is 64. Okay, so I guess it should be 32 here. No, we are moving byte wise, so it is written al. Okay, same thing from here to here, it's all the same. Okay, SI is initiated with 8000, DI with 9000, CX with 6400, AL, increase SI, increase DI, and loop. Okay, so while writing loop, the advantage is that it will decrease CX automatically. Okay, loop command always works not with CL, it works with CX, so you have to be careful with this. Okay, so this is the error which many of you do in the exam, you'll end up losing a little bit of partial marking, right? So it is always loop works with CX. So if you just initiate only CL, and if there is some spurious data available with CX, the loop will not come to 0 when the CL goes to 0, because if there is some data available in CX, it will keep continuing reducing the CX subsequently. So you have to be very, very careful with that. So it is always CX and not CL, and remember that aspect. Okay, and then do an halt operation once it finishes with the 100 bytes of transfer. So we can use a loop. Okay, so better option is to use a word and then a loop. Okay, so that will use a lesser number of cycles. Okay, but using a loop or using a jump, it doesn't make any difference, because a loop is actually to decrement CL, and it is consisting of these two actions. Okay, these two instructions are combined as loop. So using a loop only simplifies and makes your code look smaller, whereas it is not going to change the number of cycles required. Whereas word and byte transfer, it straight away cuts down your time required for execution. Okay, so whereas loop just makes your code look smaller, so you should try and use a loop also, a loop and word together. Okay, so that is how we do. And then we have also learnt about string, right? So this is a program using the string operation, where we know what does the string operation do is move SB, it moves the data from SI and DS combination to ES and DI combination. Like this is the source index, that's why this is known as the source index, and the name comes from these string operations. It is source and destination, but for the source it is DS, and for the destination it is ES. Okay, and it is very much possible that since this is to be done within the same data segment register, so we can always have a totally overlapping DS and ES. Okay, it is permitted. This also we discussed in one of the theory classes, that this is permitted. You can have memory DS and ES, you can feed in with the same data, so it doesn't matter. Okay, because the program will just calculate the physical address accordingly whenever you give a command. So now in this case 9000, it will take ES, but since in ES we have already loaded the same data segment value, so it will accordingly calculate the physical address. Okay. So it will calculate the same physical address out here, so you can do that. Now we need a counter, so we have taken it as 0064, and then we need to specify the direction, because it is going to be from 8000, it is next memory location, SI and DI have to increase. So that is why to set the direction we do this clear D. So the flag register, direction flag register will be set to 0 accordingly. Okay, so it will be reset to 0 accordingly. So this command is also very much essential. So once we write a rep, it will automatically keep repeating this instruction by reducing the this counter CX value. Okay, again remember it is CX and not CL, so we need to be careful with that, right? So we can also do a word transfer here again. Okay, so the only change which we need to do is, can anybody say what is the only, in fact two changes are required in this code to make it a more efficient word transfer. Anybody can make a guess, no problem. even if you are wrong.
So move SW and
Yeah. And one more thing, we need to change the value of
CX
the
32.
32, right? And this repeat command will automatically increase SI and DI by 2. Okay, it will do by 2 2. Okay, the way it will keep changing by SI plus 2, it will do of its own, okay, every time if the counter is not 0. So that will take care of the string operation, right? Here what is being done here, I think it is the same thing with the word. Okay, how we can, so this is one of the most simplest code which we can write for this data instruction. Okay, after having read this 5 variations, this is the best option available to us. Okay, and this is one more problem. Write an ALP that the save the contents of 8086 lower byte flags in the memory location having an offset of 1212, and then to reload the flag contents from the memory location having an offset of this. Okay, so from the flag, so once you say the flag, the operation no, the instruction is load, okay, flag, okay, into the AH register. Okay, we can do that, or we can store the flag also. We have that option also, but here we are using load. So in the accumulator, the data of the flags will be loaded here. Now if you see, only the control flags will not be affected in this case. Only the normal arithmetic flags also only will come here. There are 3 control data also available, right? Interrupt, and then a direction, and one more is I don't remember what's the third one. If you remember, it is one is about the direction, one is about the interrupt, and there is one, the third one is the trap. Yeah, trap. So these 3 data doesn't get affected, okay, when we are loading it into the AH register. So rest of the flags data will be available into the AX register. Okay, and then after that, once we move the from to this, so from AH we can transfer it to 1212, this memory location, and then again to get back we need to get the new data into the flag register. So this is the offset wherein the new data is available, so we get it that into A, and then we store it into the flag, right? So and then you give an hold command. So this is the way we go about amending the data of the flag, right? So this is an I think that's all. So rest of you have an exam on Saturday, right? So go through all these lecture notes and tutorials. I think question will be pretty simple. So there will be some program questions based on these small programs. So just go through all the instruction sets. I think that we will be able to score well if you go through all the lecture notes. Okay. So thanks a lot. If there is any doubts, then you can ask me.